This is the explanation video of the fifth experiment. Uh, so the first question is loading and generating datasets. The code uses sklearn.datasets to create different toy problems. XOR a classical logical problem that a single layer model cannot solve. Moons and circles, non-linear datasets were classified are intertwined and concentric. Iris, a real-world dataset for classifying flowers based on measurements. Defining independent x and dependent y variables. This is the second question. In these data sets, x is a matrix of coordinates or physical measurement. Y is the ground truth. For multiple class problems like iris, the code uses one hot encoding to convert class numbers 0, 1, 2 into binary vectors like 1, 0, 0, which allows the model to calculate probabilities for each class separately. The third question is data standardization. So here that is the standard scaler is applied to the training data. It calculates the mean and standard deviation, then shifts the data so it's centered at zero with a spread of one. This is critical for MLPs because it prevents a gradient explosion where large input values cause the weight to spin out of control during training. The fourth question is train test split. So the code uses a train test split with stratify parameter. This ensures that both the training and testing sets have the same percentage of each class. By keeping 30% of the data hidden during training, we can objectively see if the model has learned the logic of the data or just memorized the specific points. The fifth question is a multi-layer perceptron architecture and activation functions. The multi-layer perceptron class defines the brain of the model. Layers, you can define how many neurons are in each hidden layer. Example 2, 4, 1, etc. Activation. The code implements RELU, rectified linear unit, for hidden layers to allow for the last learning. The sigmoid for the output layer to squash the final result into a probability between 0 and 1. The sixth question is parameters and weight initialization. Weight aren't just set to zero. The code uses Xavier chloride initialization. It calculates a random range based on the number of inputs and output neurons in a layer. This Goldilocks approach ensures the signal isn't too weak or too strong as it travels through the network. Training via back propagation is the seventh question. This is the learning phase consisting of two main loops. So, forward pass. Data flows through the weights is transformed by activation functions and results in a prediction. The model uses binary cross entropy to measure the distance between its guess and the actual answer, which is loss calculation. Backward pass. Using calculus, the model calculation the gradient, how much it needs to nudge each weight to make the error smaller next time. The eighth question is plotting the training curve. By tracking the loss history after each epoch, the code generates a line graph. A downward sloping curve proves the model is converging. If the curve flattens too early, it might mean the learning rate is too low. If it bounces around, the rate might be too high. Testing and decision boundaries. To visualize success, the code creates a decision boundary plot. It colors the entire background of the graph based on what the model thinks the area represents. This allows you to see exactly how the MLP sees the world and how it separates the different classes. The tenth question is performance analysis. Finally, the model is evaluated using a confusion matrix accuracy. Overall accuracy defines the overall correctness of the model. Precision, recall, and FN. These helps understand if the model is biased. Example, if it's very good